Welcome back to the module Waves. In this unit, we'll be discussing traveling waves. Traveling waves are waves that are oscillating both in space and in time. So first we go back to the temporal wave, and this is what we have learned with the harmonic oscillator. The temporal wave is a wave that is described by u of t is capital A times sine omega t plus phi, where I now have substituted u for our extension x. So we have seen this wave, and it's an oscillation in time with a period capital T. This is the repetition in time, and a temporal frequency omega is equal to 2 pi over t. This is the rate of increase of phase per unit of time. Now similarly, you can also think about spatial waves. For example, in this sand dune, there's a spatial variation of the amplitude. These are these small ridges that we can describe also in a similar fashion. So for example, the general solution for a spatial wave is called ux. U is the amplitude, x is the spatial coordinate, and then it's quite similar. It's capital A times sine kx plus phi. Now in this case, the repetition in space, the period, is lambda, and the spatial frequency k is equal to 2 pi over lambda. This is the rate of increase of phase per unit of space. And note here that this k is not the same as the spring constant we have defined for the harmonic oscillator. Okay, now you might wonder, are there also waves that occur both in space and in time? Yes, is the answer. So now consider our harmonic oscillator. Instead of being freely able to move, it's now in a chain of all kinds of other oscillators. And it starts to oscillate at frequency omega. Now of course, the position of the harmonic oscillator is also influenced by the position of the other oscillators. Because in Hooke's law, the force that the oscillators apply on each other depends on the distance between the oscillators. And so what happens is that the temporal motion of this particular oscillator, for example U2, depends on the position in the chain. Now you can show that for an infinite chain, so with many different coupled oscillators, that we get also a wave pattern in the chain. So a spatial wave in the chain. But only if the spatial wave pattern also moves throughout the chain. So I will not go into all the mathematical details, but I will give you the solution, and that is the general solution for a traveling wave. U as a function of spatial coordinate x and temporal coordinate t is capital A times sine kx plus or minus omega t plus phi. So kx is the spatial part of the wave, and omega t is the temporal part of the wave. So how does this solution look like? So if we look at this wave now in space, we see that it's a traveling wave that travels through space, and it has a repetition in space with wavelength lambda, and a repetition in time with period capital T. And also we can see that the wave now moves in time with a speed v is equal to omega over k. Okay, let's consider now a little bit of a special example of this traveling wave. Now consider I have a rope, and at x equals to 0 I start to drive the rope with an harmonic oscillation. So u of x is 0 for larger times than 0 is equal to small a sine omega t. So I start to drive it. Now what is now the solution? Now when I start to drive it, this wave oscillation in space starts to propagate through the rope, and for x smaller than v times t, so the distance that the wave has traveled, I get the solution minus a sine k times x minus vt, and for distances larger, the rope is still in rest. So it's easier to look at it in some graphs that I made for you. So here you can see the traveling wave in space. So I started to move it at t equals 0 with an harmonic oscillation, and then it starts to move away from me. And so the points that are furthest away from me, they just start to move, kind of to feel this harmonic oscillation and start to move upwards. But the points closest to me have already made quite a few of these oscillations. And so this wave essentially is now an oscillation in space that travels away from me. Now, how does this look in time? So then we look at this specific point, for example, the point at 50 meters. So here you can see what happens to this oscillation at this particular point 50 meters away from me. So the first half a second, nothing really happens because I start already to oscillate, but this wave hasn't arrived yet at the point where I'm looking at. But after half a second, also now the oscillation has moved through the rope and the oscillation starts to go upwards at this particular point and then follows a harmonic oscillation in time. So we have now described this propagating wave, this traveling wave, as a function of u, as a function of x of t. And this is a very general description for a traveling wave. So in this case, u can be both a longitudinal amplitude, so an oscillation in the direction of propagation, but it can also be an oscillation perpendicular to the direction of propagation. It's what we call a transverse wave. In this case, the oscillation is like that, but the wave is actually propagating in the forward direction. Now, wave phenomena occur in many parts of physics. So there can be traveling waves, for example, in liquids, for example, in sea, or in solids, for example, with earthquakes, or in gases. This is part of the acoustics, or even waves that travel through vacuum, such as electromagnetic waves, or even waves that travel through space-time, such as gravitational waves. All these propagating waves, these traveling waves, are described by this kind of the same physics and mathematics. So in summary, I've told you about the traveling wave that is described by this formula, and that the traveling wave can have both oscillations in space and in time. And furthermore, this formula and this equation describes both longitudinal and transverse propagating waves.